Okay, so I'm going to walk you guys through the lab that we did based on Charles' law, where we're looking at the relationship between temperature and the volume of a gas. And so this is the data table that you guys had during the lab, and I'm going to make sure that you understand where all these different values came from, exactly what you should have been able to do with these numbers, and then what the numbers actually tell us in terms of what is that relationship between temperature and the volume of a gas. So make sure you guys watch the video that I sent out earlier that shows you the procedures so you can remind yourselves if you don't remember. But these don't necessarily go in order of what we actually did. So the first thing that the data table has here is the volume of water that was forced in the flask. This is actually one of the last things that took place during your lab procedure. And if you look at the data that you did have, it should be a relatively small number. We're not looking at anything huge here. And in fact, the data that I collected for you guys, I had only 25 milliliters of water that actually flowed into the Erlenmeyer flask when the flask was in the sink after it cooled off. The initial volume of the air, all this is asking you is to figure out how big the space was inside the flask. Now it was a 125 milliliter flask, but that's not how much air was in there, because there's more space inside that flask than there are above the markings where the top of the flask is. So the way that we did this one is we had to fill this up complete with water. We reinserted the stopper to push some of the water out, just so that it was in the same position that it was when we were heating and cooling it. The flask that I use is going to be maybe slightly different than yours, but they all should be relatively close to each other. When I filled my flask up and then measured the amount of water that was in there, I got a total volume of 149 milliliters. The next step here talks about the initial temperature, and so this is actually the temperature of the hot water. So that was the temperature of the air. How is that the same thing as the temperature of the water? Well, we had to make an assumption. The reason that you let the flask sit in the hot water, the boiling water, at least the warm water, for several minutes was that we made the assumption that that was enough time for the air inside that container to come to the same temperature as the temperature that was in the water. Now, I had a little bit more time than you did while we were running this, and so my value was somewhere around 99.5 degrees. And then the final temperature of the air, which is the temperature of the water in the sink, same rationale. We put the flask inside the sink, we let it cool off for a few minutes, and then we made an assumption that the temperature of the water was then equal to the temperature of the air that was inside that flask. My temperature was 20.5 degrees in the sink. We haven't discussed this in detail yet, but one thing that you'll see here is that we're asking for the Kelvin temperature. And the way that you get Kelvin from Celsius is simply by adding 273. So if we look at this 273 plus 99.5, we're going to have a total of 372.5. And if you look at 20.5 plus 273, we get 293.5. So what we're going to figure out later on as we start discussing the details of the gas laws is that we're going to use the Kelvin temperature scale for every single gas law calculation that we do. This last step here is asking what the final volume of the air was, and so how much air was actually left inside our flask, because when we heated the flask it was open, and when the air rushed out and then we cooled it back down after we sealed it, there was less air in there than what we had before. How much less air? Well, this value is how much water rushed in. This amount of water that rushed in is equal to the amount of air that left. So to figure out what the final volume of air was, we just do 149 minus 25, which in this case will be 124. So all of this information that we have in the top part of our data table, this is all from the experiment. So we call this our experimental data. So Charles' law, just like any of the other gas laws or any other scientific law that we've studied or will be studying, they have predictive power. Theories can explain why things work. Laws are able to provide predictions for us. So if we look at this formula right here, we can see that this is a rearrangement of Charles' law, and that law is showing us really a comparison between the initial volume and temperature and the final volume and temperature. In this case, we were looking for the final volume. We discovered our final volume to be 124 milliliters from a warm container cool down to a room temperature container. So these conditions up here, where we had the 99.5 degrees, this was our initial steps. And so the gas is bigger, it took up more space then. As we cool it down, the particles slow down, they get closer together. We found an answer of 124 milliliters, or a change in 25 milliliters. Well, what should that have change have been? And that's where this law can help us figure that out. So our initial volume here, we know that the initial volume was 149 milliliters. And if we follow the formula above it, we can multiply that by the final temperature, which was 293.5. All this information is coming from our data table just above this. And then we divide that by the initial temperature, which is 372.5. This is temperature in Kelvin. This is temperature in Kelvin. So if we find this answer right here, that should give us what the final volume should have been. This is what our predicted final volume would have been. And if you plug that in your calculator, you should get a total value of 117.4 milliliters. So that's not quite 124. So how far off were we? And this is where this final step is, allowing us to compare what the actual value should have been as compared to the experimental value. So if we move down the page a little bit, what was our experimental final volume from our data at the end of the experiment? Was 124 milliliters. According to Charles' law, what should the final volume have been? It should have been 117.4. What is the difference between 124 and 117.4? It's a total of 6.6 milliliters. And then we want to figure out the percent error. The way you figure out percent error is you take the difference and you divide that by the actual, which in this case is from Charles' law. So from Charles' law. So we got our 6.6, divide that by 117.4, and that gives me an answer of just over 5.5%. So if we use our kind of standard 5% rule, we're pretty close. What sorts of experimental error can get involved in this one? I'll let you guys think about that, but I hope these calculations are a little bit easier for you. You can use your data and figure out how close you guys actually were to what you should have gotten during the lab. Thanks.